This is an introduction to the Maxwell-Boltzmann distribution. I hope you find this video helpful. So first, I'm gonna briefly talk about the energy expression that has Boltzmann constant. Then I'm gonna show how the Maxwell-Boltzmann distribution, or just Boltzmann distribution in short, is derived mathematically. And then I'll talk about the partition function in depth. The partition function is part of the Boltzmann distribution. Then finally talk about the distribution as well. So here, the ideal gas law. And some of you might know already that this law describes a system. It could be your room or a container or the entire earth or even the sun, anything. And we will say that the system has a fixed pressure and volume for simplicity. If you think about their unit, pressure is force divided by area, so newtons per meter squared, and volume is just meters cubed. So P times V is newtons times meters, which is equivalent to joules. So here we know that this law is talking about energies. And this energy corresponds to the entire energy in the system. Makes sense, right? Because we calculated from the pressure and the volume of the system. Now there's this equal sign, which means the other side is also in joules. It's an energy. Okay, so far so good. So where does all the energy come from? It's probably from the substances that are forming the system. Let's talk about the substances now. This N is number of moles. So if it's 1, for example, 1 mole of hydrogen atom, that means we're actually talking about 6.022 times 10 to the 23 hydrogen atoms. Or if it's 2 moles of water molecules, that's actually 1.2044 times 10 to the 24 water molecules. So it could be particles or molecules, doesn't matter, right? So whatever substances are creating this system, if we want to talk about the actual number of substances, it would be better to have this expression instead of the number of moles. So N is the actual number of whatever they are, and the ideal gas constant R divided by the Avogadro's constant is redefined as Boltzmann constant. Okay? That's a universal constant that can be applied to anywhere in the universe. Now, the number of substances doesn't have any units, right? It's just a count of something. So that would mean the rest, kT, must be the energy. This is the unit energy. So one tiny substance contributes 1 kT of energy. 2 substances contribute 2 kTs of energy, something like that. All the way to the total amount of energy. So again, each substance contributes 1 kT of energy to the system. Let's look at an example. A cylinder that has a volume of 100 meters cubed is filled with nitrogen gas. So the cylinder is the system, okay? And the pressure inside the cylinder is measured to be 50 kilopascals. Then what's the total energy in the cylinder? Easy. Now, the temperature inside the cylinder was found to be 100 kelvins. Then what would be the amount of energy that one nitrogen gas molecule contributes to the system? As we learned just before, each molecule should have 1 kT of energy, right? And finally, how many nitrogen gas molecules are inside the cylinder? Using the ideal gas law, we find that there should be 3.62 times 10 to the 27 nitrogen gas molecules in there. Does it make sense? Again, kT is the amount of energy from one substance, in this case, one molecule. Here we have another tank. It's a different tank that has the same pressure, but the temperature inside is higher. Now, how much energy would one nitrogen gas molecule contribute to the system? It's kT, so probably 3 times more than the ones in the previous cylinder. And how many molecules are inside the cylinder? Can you guess? The number of molecules decreased. This totally makes sense because to reach the total energy of 5 times 10 to the 6 joules, we won't need as many molecules as before because each molecule contributes a lot more energy to the system, right? So we should have less amount of gas there, and it should still have the total energy of the same amount as before. So this was a quick review on the ideal gas law. What we need to remember from this is that kT is a unit energy in the system. We have a system here that contains n particles. These are the same type of particles, but they're distinguishable. So we know which one's particle A, which one's particle B, and etc. And we're gonna make assumptions here. It's a large system, and the system is in thermal equilibrium, such that all particles move around at the same speed. Then, for example, you put your hand inside the system and randomly caught one particle. What would be the probability that the particle you caught is particle A? 1 over n, of course, because they all have the same probability. Same particles in the same condition, so makes sense. How about the probability of catching particle B in the system? It should also be 1 over n. Now, how about the probability of finding both A and B? It should be 1 over n times 1 over n minus 1, right? But we had the assumption that n is large, so we can say that it's roughly 1 over n squared. Agree? Now think about our result. 1 over n squared sounds like the product of two separate probabilities, if you think about it. So, this is something that we can use when we assume that n is large and the conditions are the same throughout the system. Ludwig Boltzmann, the Austrian physicist, called this equal a priori principle, and many mathematicians and physicists at that time didn't like it. They thought Boltzmann is being careless and sloppy. In fact, Boltzmann tended to assume many things, but apparently he has contributed significantly to the math and the physics field. So I brought the equation here. Let's talk about this in more detail. In thermodynamics, the system that I just introduced that had large n and is in thermal equilibrium, physicists call it a heat bath. Why? No particular reason. The name just sounds right. And here I showed ensembles instead of particles. That's because it could be particles or atoms or molecules. They could even be individuals or chunks. Doesn't matter, as long as the applied conditions are the same. But the number of substances in each ensemble could be different. Like ensemble A could contain 3 particles, when ensemble B contains 5 particles. So the amounts of energy are different. And again, n is large here, so no matter how different they are, all the energies are a lot smaller than the total energy, okay? Alright, that was a bit long introduction. Now that we're talking about the energies, I'll rewrite it this way. Let me just put derivatives on both sides. If we're taking the derivative with respect to E1 here, we should do the same for the other side, right? If we're doing it with respect to E2, the other side should also be done with respect to E2. Nothing interesting so far. Also, I'm gonna name each side like this. Left-hand side 1, right-hand side 1, left-hand side 2, right-hand side 2, okay? Let's first look at the left-hand side. Left-hand side 1 in particular. I'm gonna multiply both the numerator and the denominator by this. Nothing wrong about that. And just like chain rule, I'm gonna switch the denominators. Now, what's dE1 plus E2 over dE1? E2 will simply disappear. So dE1 over dE1 should be 1. But then, doesn't that mean it's okay to write it this way? dE1 plus E2 over dE2 is also 1. Yeah, that's the trick. If we switch back the denominators, we can immediately tell that this is basically the left-hand side 2. So left-hand side 1 and left-hand side 2 are equal, which means left-hand side 1, left-hand side 2, right-hand side 1, right-hand side 2, they're all equal to each other. So let's put this aside for a moment and move on to the right-hand side. Each derivative means this, right? assuming they're independent variables. Then as we found out that all sides are the same, they should be the same too. At last, we obtained an equation that we need for deriving Boltzmann distribution. That's what we needed. If I rearrange it by putting the same variables together, this means it could be the same for E3 and E4 and etc. Again, the amount of energy may vary, but nevertheless, they're all small compared to the total energy. So the rates are all roughly the same. You remember from here, how you could say that 1 over n times 1 over n minus 1 is roughly 1 over n squared? I'm talking about that, okay? So back to here. As they are all equal, we can generalize the expression this way. I'm gonna give a name to the constant, beta. Why is there a negative sign? It just helps in some way. I'll explain you later, so don't worry. And why not? It's just a constant. So if anything, we could simply say that beta itself is a negative number, right? Nothing mathematically wrong about putting a negative sign there. Now, you've studied differential equations, so you should know what happened here. If you can't understand, try to go backward, like do this derivative. You'll get this back. It'll make sense. So I'll continue. Let's integrate both sides so we can get rid of the derivative. C is the constant term from that integral. Take a moment and make sure you follow everything. Now let's talk about this expression. We have negative beta e sub n as the exponent. Can exponents have units? No. How can exponents have their own unit? It's mathematically impossible. This means this whole thing must be unitless. Then what would that mean? It would mean that beta is the reciprocal of energy, so the units cancel out. Let's finally bring the knowledge that we obtained from the ideal gas law, an energy expression that relates to temperature, kT. Yes, our constant beta is gonna be the unit energy, so that the exponent here becomes dimensionless or unitless. Yay, we used our knowledge here. Good job to us. So this is a negative exponential function. And think about it, negative beta made sense. Because when we had more energy, the probability went down. Like for probability of just E1 was 1 over n, but probability of E1 and E2 at the same time, it was 1 over n squared, right? The probability was decreasing. So this is why we had negative sign, just to make sense. Lastly, we have this normalization constant to solve. This is a probability. So if we add all the probabilities, it should equal to 1, right? There, we found our constant. This sum of all probability factors has a name, z. This is called a partition function, and it's just for normalizing the probabilities. But physicists have discovered that this z tells us a lot more about the system than we thought. You'll be shocked. I mean, it's just the total probability factor. How is this useful, right? Anyway, for now, let's confirm. So this is how it should be. And now we have a full expression of the probability. This is the Boltzmann distribution, named after Ludwig Boltzmann, poor guy who had to face significant criticism throughout his lifetime. Yay, we have derived the Boltzmann distribution by ourselves. So this distribution is also called Boltzmann-Maxwell distribution, because James Maxwell, the Scottish physicist, was a contributor. And in the future, you'll learn about Fermi-Dirac and Bose-Einstein distributions, which look very similar to the Boltzmann-Maxwells. They're the quantum mechanical versions of the Boltzmann-Maxwell distribution. You can think it that way. So they are more exact expressions. For your interest, at energy equals 0, we get the following numbers. The graph just looks beautiful. And if you think about the Fermi-Dirac's and Bose-Einstein's versions, in the classical limit where n is large but still much smaller than E total, the exponential term will be a large number, so plus minus 1 will be negligible. Then we retrieve our Boltzmann-Maxwell's factor. Didn't we assume that E sub n is small? Yeah, you're right. Like I said, it's still much smaller than E total, but what I'm saying is if E sub n is large enough that quantum mechanical effects are insignificant. So how small are we talking about here? Yeah, a lot smaller. Fermi-Dirac and Bose-Einstein's distributions are for extremely small amount of energy. Okay, that's enough about the Boltzmann distribution for now. Let's move on. Let's try to understand the mathematical meaning of this probability expression. When we think of probabilities, we think of this. What's the probability of picking a green ball from the back? 3/6. How about a red ball? 2/6. How about a blue ball? 1/6. We know that these fractions are just the number of balls over the total number of balls, literally, right? And look at the Boltzmann's probability distribution. It is a fraction, so that's a good news. One might wish that this is a ratio of some number to a total number. Well, surprisingly, they kind of are. Now that's great news. The numerator represents the number of energy states for occupations, and the denominator represents the number of the energy states available in total. Like, just literally, they are counts. You don't believe me? But before that, what are the energy states that we are talking about? You remember this energy level diagram from high school chemistry? Like, those are individual energy states. Let me give you an example. Before I start, I just want to let you know that this is a super simplified version where I'm ignoring the fine structures and stuff, okay? What's the probability of a particle's energy being at the 3D state? So the total number of states is 1, 2, 3, 4, 5, and there's 9, so 5 plus 9 is 14. And plus 5 here, so that's 19. We have 19 states in total. And the 3D states are 5 of them. 5/19, that's the probability for the energy to be in that state. And what I'm saying is, here, if you compare, this 19 is the Z. And 5 is the exponential term on top. You might be asking, but hey, the exponential term could also give us a decimal number. Yeah, I know. It could be a decimal, like 5.2 states over 19.1 states or something. This would mean approximately 5 states over 19 states. This is why I said they kind of are. They kind of represent the number of states. Because they might not be integers, but they still really are the number of states. Just like how those numbers literally represented the number of balls, right? It'll become more clear later, trust me. Alright, before anything, let me ask you about something. I brought random atoms here. You know that the hydrogen atom has only one electron orbiting around the nucleus. Does this mean the electron of the hydrogen atom can only stay in the 1s orbital, the lowest orbit? How about the carbon atom? Carbon atom has 6 electrons like this. Does this mean only these 2 orbits are available for the electrons? Like, can't they go somewhere else? For those who didn't know until now, every atom can have up till 7 different levels or 7 different orbits. It's just people draw only the orbits where electrons are orbiting. We're just too lazy to draw 7 different circles every time, right? That's really the truth. And one more thing, it's 7 levels because in the periodic table, we have 7 energy levels. According to the periodic table, there can be 118 energy states, right? So, if every atom can have all the energy levels, shouldn't Z always be 118 then? The answer is no. I never said all the energy levels are always available. If you want an electron to go to a higher orbit, you need to provide energy to it. If the environment is cold, the electron won't have enough energy to be excited from the ground level. So this 118 is the Z maximum. This is not really the number of energy states available. Let me show you something. Here, I tried my best to draw the energy states of an atom. I'm using the hydrogen atom as an example. By the electron configurations, in the first orbit, we can have 2 electrons, right? In the second orbit, we can put 8 electrons. I'm talking about the Lewis structure. So in the third orbit, 8 again. And in the fourth orbit, we can put 18 electrons. Like 2 spots from s orbitals, 6 spots for p orbitals, and 10 spots for d orbitals, and so on, okay? And the reason why I colored the first orbit in yellow is that at the moment, those are the available spots for an electron. The temperature of the atom is low at the moment. Z in this case is 2. Now I'm gonna increase the temperature a little. The place is hot enough that now we can put an electron in the second orbit as well. There are 10 available spots for the electron now. Z equals 10 in this case. So the electron has enough energy to go to the next level. It hasn't gone there yet, but I'm just saying it is possible to go there now. So if I increase the temperature again, more spots are open for the electron to enter. The electron will have 18 different options. So when the temperature is extremely high, so high that an electron could go to any orbit, that's when every atom will have the Z value of 118. Does it make sense now? If this video so far helped you understand better about the concept, please like and subscribe to my channel. Okay, so I'll continue. Why don't we simplify the situation? Let's just forget about the degeneracies and say that each level has only one accessible spot, okay? Just for simplicity. So this is gonna be our energy level diagram. This is simplified energy levels of the hydrogen atom. Physicists can obtain these numbers through the experiment. K here is the wave number, which is 2 pi over lambda. So if we want to relate these numbers to their energies, we just have to times it by the Planck constant, h, and the speed of light, c, okay? So as you can see here, K and energy are proportional to each other. And these numbers are basically related to the required energy for an electron to reach those states. Of course, the electron won't need any energy to be at the bottom, so E1 is 0. Like I mentioned previously, Z can have 7 different exponential terms because of 7 different energy levels, but let's just shrink it to 4 for simplicity, okay? So if we plug in the required energy for each term, the only variable left is the temperature, you see? Now, if the hydrogen atom is cold, T is gonna be a small number, right? The first term will still be to the 0, no matter what, but the other term's exponents will become large numbers, because T is in the denominator, right? E to the negative some large numbers should be small numbers. So we can approximate them as 1 plus 0 plus 0 plus 0, which is 1. Z is approximately 1. This means because the hydrogen atom is cold, the electron won't be able to excite to another state. Like those high energy states are not available for the electron. We only got one available spot here, Z equals 1. Let's heat up our hydrogen atom. This means we'll have these. Let's say the temperature is high enough that the low numbers are very close to 0. Then we'll now have all the terms surviving. 1 plus 1 plus 1 plus 1, approximately, which equals 4. Z is 4, which means there are 4 available spots, including the ground spot, for the electron to go. This is why I said Z roughly corresponds to the number of energy states available. It could be a decimal number, but that's okay. In the end, we just need to know the ratios in order to calculate the probabilities, right? So in real world, we have degeneracy. So Z is simply the multiple of each term combined. And in case the temperature is high, that's 118. Oh, here comes the last important knowledge for us. So far, we have only talked about the denominator, the partition function. Now it's time to talk about the numerator, which is the probability factor. From now on, we are going to assume that the temperature is fixed. We cannot heat up an atom. We're only going to talk about the different energy levels. So since the numerator is also an exponential function, like the partition function, if the required energy is high, that means e to the power of a negative large number, which means a low probability. This is obvious. I mean, if the threshold is high, it's difficult to achieve. So that's that. And one more thing to remember. Even if an electron does have enough energy to get to a higher state, it doesn't mean it will go there 100%. Everything is probabilistic. So there still is a chance that it stays in the ground state, not using its energy. It's like this. We have a hotel that has different types of room. Just because you have enough money for the luxurious room, it doesn't mean you must go there, right? You can still stay in the cheap room. So that's what I mean. So let's talk about a system in general that has different energy levels. It could still be an atom, a particle, or a molecule. It doesn't matter. And we're given this ensemble of particles to put in. As you can see, the energy levels are low and are close to each other. So at a fixed temperature, you see there, they should all be e to the power of roughly the same number. This means the probability of each energy level being occupied by the ensemble is 1/3, 1/3, and 1/3. All three states have the chance of being occupied with equal probability. Now, imagine the system has energy states far separated from each other. The bottom one, of course, requires much less energy than the other two. So let's say it just dominates the other terms. Then the probabilities are gonna look like this. So almost 0 for the upper state and almost 100% for the lowest state. This just means it's certain that the ensemble will stay in the lowest level because the other levels are too high to reach, which makes sense. So this is the last example I'm gonna show. I'll stop showing everything with only zeros and ones. Let's be a bit more realistic. Say we have two low energy levels and one high energy level, and the probability factors were calculated to be these. The partition function is 7.201 if you just add them all up, which means there are roughly 7 energy states in total. You see, this is why it's statistical mechanics, because we are kind of counting them and calculating some probabilities. The probability of each energy level being occupied by the ensemble is so the highest energy level is too high to reach, but the second floor is fairly close to the bottom. There is about 26.4% chance that the ensemble occupies this level, and there's 73.6% chance that it'll just stay in the ground state. And again, just because we have enough energy to go to the second floor, it doesn't mean we must go there. Just like even if you have enough money for the luxurious hotel, you don't have to go there. Unless we have a lot more money to consider about the upper levels. So in this case, increasing the temperature is like increasing our budget. Finally, here's the bonus fact. You might be hearing this a lot, that the partition function is such an important thing to know in thermodynamics. But why is it so important? If you know Z, you can calculate for almost everything about the system. Hey, subscribe. Thanks.